you do number 50?
50 from the problem set?
Yes.
Sure. Grab that real quick.
Oh, thanks, boy.
Okay. So what we're going to start by doing is we're going to observe that I know I'm looking for 4 solutions. Again, because this says all of the zeros, I know I'm looking at real, imaginary, irrational, multiples. So there's 4 total if you count everything. So now we'll start by doing our rational roots theorem and figuring out what are the possible rational zeros. So those are going to be factors of the constant term divided by factors of the leading coefficient. Since the leading coefficient is 1, it's just going to be factors of the constant term. So the factors of 64 are 1, 2, 4, 8, 16, 32, and 64. Now, to figure out which one of these I'd want to start my synthetic division with, I'm going to look at the graph, and I'm specifically going to be looking for the x, or looking for x, or where the x-intercepts are. So I'll just graph x to the 4th plus 12x squared minus 64. And I'll graph that on just kind of our standard window. So it looks like -2 and +2, I see some x-intercepts at. I notice that in each case, I have -2 and +2 are on my list of possible rational zeros. So those are good things to do synthetic division with. If they weren't on that list, I would not want to use them to do synthetic division. So it doesn't really matter which one I start with. So I'm just going to start with -2 because I listed it first. So I'm going to start the setup for my synthetic division. To write the numbers on the inside, I have to be quite careful here, because if I look at my polynomial, I notice I'll go from x to the 4th to x squared, skipping x cubes. And then I also go from x squared to a constant term, skipping x's. So I need to account for that when I do my synthetic division. So I'm going to put a 0 for the x cubed that we skipped and a 0 for the linear piece that we skipped. And I have to have those in there, or the synthetic division is not going to be giving me the correct answer. So I'll bring this down, and then I'll just go ahead and grind through my synthetic division here. 32. So I got my correct answer there. That's good. The problem here, though, is what's this remainder going to be? What degree polynomial is this remainder? Stop talking, please. It's a degree 3, right? Because I have constants, x's, x squared, and x cubed. And I don't know how to solve a cubic polynomial, so I'm going to do another synthetic division now. So I'm just going to do the 2 now, and I'm just going to take those answers and just do another synthetic division. And that one worked. So now the result that I have left is constant x, x squared is quadratic. This I feel good about because I know I can solve any quadratic. So the way this is going to factor is I'm going to have an x plus 2 because negative 2 gave me a remainder 0. I'm going to have a x minus 2 because 2 gave me a remainder 0. And then I'm going to have a x squared plus 0x plus 16. I'm not going to bother writing the 0x like that. Does that feel so good? So far, so good? This I can now set equal to 0 since I'm looking for the zeros. And I can apply the zero product property to set each factor equal to 0. So over here I get the solution negative 2. No doy, I saw that on the graph. Here I got the solution positive 2. No kidding, I saw that on the graph. Here, to solve x squared minus 16, I could use the quadratic formula. That would be fine. But I could also just solve this directly because there's no regular x term. So I would just subtract 16 from both sides and then square root both sides. When we square root both sides, we get the plus or minus. Because we're square rooting a negative, I get an I, and then the square root of 16 is just 4. So that's 1, 2, and then 3 and 4 solutions. I have 2 solutions there because one for plus 4i and then a second one for minus 4i. Does that feel good? Again, like, not super difficult, anything that you're doing, but the process is a little bit lengthy and can be a little time consuming. But the key is, making sure that you're using your graph to figure out what you need to do the synthetic divisions with, and then you do the synthetic divisions until you get a quadratic piece as your leftover. At that point, you can stop doing synthetic divisions because you can solve any quadratic using the quadratic formula, if not some other method. Does that feel good? Cool. Juan?
Can you do
43? Sure. So here it says, again, find all the zeros for the function. Is the process I'm using going to change at all? No. No, not a single bit. So I know how many solutions am I looking for? 3 solutions, right? Because it's a degree 3. Now, my possible rational solutions, oh, Billy, I got a bunch of them, right? So 16 has the factors 1, 2, 4, 8, and 16. Yes, 12 has the factors 1, 2, 3, 4, 6, and 12. Yuckarooskies, right? But if you look at the coefficients here, you can actually make your life a whole lot easier. If I look at the coefficients, what do you notice about all of them? They're all divisible by 4. So really, I can just treat the leading coefficient as 3 and the constant term as 4. Oops, put them in the right place. So like those guys go and those guys go, and that's a much nicer list. So I have 1 over 1, 2 over 1, and then 4 over 1. I have 1 over 2. I have 2 over 2, but I'm not going to list 2 over 2 because I already have that listed because 2 over 2 is just 1. Yes, sir.
how is 2 and 3?
How is what?
How is 2 and 3? You listen to all
So the,
For the leading at top.
oh, sorry, yes, 2, thank you, shouldn't be in there. Perfect, yes, even better, right? So I just have 1/3, 2/3, and 4/3, and now I'm done. Thank you. Excellent, excellent point. Saves us a whole heap of time. Does that feel okay? All right. Let's go look at the graph. So I can type this in. I'm just going to type in the original. It doesn't really matter. You could type in the 3x cubed minus 7x squared plus x plus 4. Also, that wouldn't be wrong, but I'm going to just type in the original because if I've made any kind of mistake doing the factoring, it would then screw this part up. So if I just type in the original, at least I'll get the x-intercepts, you know, like the real ones on there for me. So I'll do that and take a look. Okay, looks like I got one here, one there, and one there. Everything looks between -1 and +2. So I'm going to actually just go zoom this in a little bit because I can't really tell very well what's going on. Okay. So what does this look like? This is 0. That's -1. I think it's less than -1/2 though. I think it's like -2/3.
Could you use trace?
Sure. You could kind of trace. Oops. Oh boy. Come on now. Oh, come on. Be nice here. So if I trace over here, you can see that that's, you know, right around there. Where did my work go now? There you are. So I would say probably -2/3 would be the one that'd be the closest. I'm going to put a question mark by that because it wasn't, I mean, it's close, but it's I'm guessing here a little bit also, right?
Really just guess.
I'm just kind of eyeballing it, yep. And let's do the next one. So what do we see over here? That one is maybe +1 1/3. By that, maybe 4/3. Again, if I want to, I can kind of trace along and see where that's kind of at. Come on. So that looks real close to me. I feel much more confident about that one. And then my last one here is, what's that, about 1.6. So that'd be like 1 2/3 would be 5/3. Now, is that a possibility? Is it on my list up here, though? No. So what that's going to tell me is that I don't want to use this one. Okay with that? And I probably don't want to use this one either because I didn't feel very good about it when I traced it through. That's going to be the one that I'm going to use.
So what happens to
If you tried using one of those, they wouldn't give you a remainder 0. So you just start over. You pick a different one and try it if they don't give you a remainder 0.
what if like you thought of like good ones?
Then I've written a bad problem because there's nothing for you to do in that case. That one's on me then. So bring the 12 down. 4/3 times 12 is 16. That's -12, so that's going to be -16. That's -12. That gives me -16, which is 0. The result here that I get is quadratic. So I'm done. I can just say x minus 4/3 times 12x squared minus 12x minus 12. And that's all equal to 0. So I set each piece equal to 0. And obviously this is 4/3. No duh, I knew that before. I'm going to divide everything by 12 here, just to make life a little bit easier to quadratic formula this thing, because now the numbers are much smaller. So what I get there is I get 1, plus or minus 1 minus a negative 4 is 5 over 2. So that's my other two solutions. And if I look at the decimal for these, if I do 1 plus the square root of 5 over 2, that's the 1.61 that we saw before. And if I do the minus, that's going to be the negative 1.6 that we saw, or the negative 0.6 that we saw before. So I feel real good about that. Is that cool? So still the exact same process, right? The tricky thing is when you get those zeros that are irrational that you can't use synthetic division on. That's why we bother making the list of rational or possible rational solutions, is so that we can detect those hopefully when they come up. And another nice thing here, Dewan, that you can use is that these irrational solutions are always going to come in conjugate pairs, so they're always going to come with a partner. So this one that we didn't like about, we could also right away be looking for it like, aha, that's probably its partner. That's the 1 minus square root 5 over 2 to go with the 1 plus square root 5 over 2. Just like the complex solutions come in conjugate pairs, the irrational ones do as well. So the irrational means it has like a square root in it, right? Does that feel good?
Yeah.
Okay. Sure, no problem. Anybody else? Okay. Well, let's start chapter 14 then today. Oops. No. So ideally, this chapter would be a review of things you did in Algebra 2. I know you guys didn't do this in Algebra 2. So we'll go through this kind of carefully and slowly, okay, because I know you just didn't get that far, which is fine. But I'm giving you a heads up that this would be designed as a review topic that is going to be an introductory topic for you guys. So let's start by just defining what a rational function is. So a rational function is just one polynomial divided by another polynomial. Okay? And we know what polynomials are. It's what we've been solving this whole last chapter, right? Okay. So all right. So if I have some rational function, P of x divided by Q of x. And I'm interested in the domain for this rational function. Let's think about what that is. Now, the domain for any polynomial is all real numbers, because if all you're doing is like adding, subtracting, and multiplying, you can never create something that's undefined. Now, rational functions also have the operation of division, right? Because you have one polynomial divided by another polynomial. Where can division get in trouble?
When the bottom is 0.
Great. When you divide by 0, when the denominator of your fraction is 0, that's not okay, right? That's what we call undefined. Those are going to be the location of the holes in our domain. So our domain is going to be all real numbers except where that denominator is equal to 0. So let's look at an example then, or examples anyways. So the first thing I want to do is check to make sure this is a rational function, right? Do I have a polynomial divided by another polynomial? Yeah, right? Those are just two linear functions. So to find the domain, I'm just going to start by taking the denominator and setting it, well, I guess I can even just say equal to 0. It doesn't really matter. Now that's easy to solve, right? What's the solution to this? 1/2. I add 1 to both sides and then divide by 2. So that tells me that my domain is all real numbers except for 1/2. How do I write that using interval notation? Do you remember how to do that? Interval notation is the stuff with the parentheses in it, or brackets. Yeah, so we'd start at negative infinity, and we'd go up to 1/2. Then we do the u for union, and we do 1/2 to positive infinity. Excellent. Yep, that's exactly right. So this would be like the way I'm going to write the answers in the key or whatever. Does that feel okay? Not a big deal there, right? We've done stuff kind of looked like this already in first semester when we just did domains and ranges of functions in general. Let's do another example where the denominator is a little bit more complicated. Okay. So here we have 3 minus x over x cubed minus 4x. Is this a rational function? Yeah, still polynomial divided by polynomial. So I'm going to take the denominator and set it equal to 0. Now I need to solve this. How do I solve something that looks like this? Yeah, we don't want to divide it out because x could be 0 and then we'd be dividing by 0. Yep, but factoring is the word you're looking for. So I can take out a greatest common factor of x. Now what about that x squared minus 4? Okay, you could just set the pieces equal to 0 because x squared minus 4 is quadratic and we know how to solve that. Sure. So when I set x equals to 0, then that's an answer, right? We didn't have to actually do anything there. And then the x squared minus 4, what do we do? Mm-hmm. Great. That's correct. All right, so how do we write our domain then? What do we start at? Okay, and where's the first hole that we get to? -2. And then from -2, where's the next hole at? 0. And then after 0, the next hole's at 2. Oops. And then we go from 2 all the way to the end. Woof! But it's easy to write once you recognize what's going on, right? Not a big deal. Once you get the locations of those holes, you just got to make sure you write them in order, right? Okay. So rational functions are very different from polynomial functions in that they have discontinuities. Well, I should say can. They don't all have to have it, but they can have discontinuities. There's 2 types of discontinuities they can have. They can have a vertical asymptote. But that's not a discontinuity necessarily, right? Oftentimes, if there's a horizontal asymptote, you can still draw the curve with a pencil, like with one stroke of your pencil. So what does a vertical asymptote look like again? Yeah, it's like a vertical line that the graph approaches but never crosses. So maybe like this, where that dashed line is the vertical asymptote. The other type of discontinuity we can have is called a removable discontinuity. Do you remember what this looks like from first semester? Just like some little hole in the graph, right? Where the graph is going along doing its thing, there's a little gap in there, and then it continues along doing its thing, right? And the way we put the little gap in there is we just draw an open circle at the point that's missing. So that guy there is your removable discontinuity. Everybody's cool with that? Okay. So that's what they look like. Let's talk about how we tell the difference between a removable discontinuity and a vertical asymptote just by looking at the equation. Okay. So for r of x equals p of x divided by q of x, if p of x over q of x cannot be reduced, the solutions to, yes, of course, q of x equal to 0 give us the vertical asymptotes. Okay. And we'll do some examples of this in just a second. Okay, so if P of x divided by Q of x can be reduced, any factors that we completely cross off from the denominator from Q of x, we would set those equal to 0 and solve. Those will give us the removable discontinuities. And any factors remaining in the denominator, set those equal to 0 and solve, will give you the vertical asymptotes. So this sounds really complicated. It is not. Okay, so let's just run through a couple of examples here real quick, okay? All right. So let's say we have the function f of x equals x minus 5 over x squared minus 5x plus 6. The directions we give for identifying these discontinuities, we need to start by checking to see if we can reduce this fraction. In order to reduce this fraction, what must we do first? Not setting them equal to 0. So imagine we have the fraction like 4 over 8. Can I reduce that? Okay, how do I reduce that? Well, I notice that the numerator could be 4 times 1, and the denominator could be 4 times 2, so I can reduce the 4's out of there, right? Correct, yeah. So what do I need then to do? What is the process of going from like 8 to 4 times 2 or 4 to 4 times 1? What is this process called? It's factoring. That's all we're doing there. So if we have polynomials, how do I factor x minus 5? It's kind of a trick question, right? Because can I factor x minus 5? No, it's already prime, right? It'd be like having a 5 in the numerator or something. Can I factor x squared minus 5x plus 6? Yes. This is the one skill you've repeatedly told me you guys practiced the heck out of last year in your Algebra 2 class. How do I factor x squared minus 5x plus 6? Great. Adds to negative 5, multiplies to positive 6. What two numbers do that? Negative 2 and negative 3. Everybody's okay there? Alexis, you had multiplies to give us negative 6 and adds to give us negative 5. Easy to make that mistake. Not a big deal. Okay. Are there any factors in common between the numerator and denominator? Well, the x isn't a factor. The factor is the parentheses, right? Is there anything inside the parentheses that are identical? No, right? There's not a set of parentheses that are identical in the numerator and denominator. So this is not able to be reduced. Right? And here's the good news. To find, well, since that's the case, I know that all I have is vertical asymptotes. And because I've already factored the denominator, I can set the factored form equal to 0. And it's very easy then to get my solutions out of it. So I know both of these are vertical asymptotes. Is everybody okay with that idea? This is the most common outcome, is when you get just vertical asymptotes only. Let's look at another example. Let's look at x minus 3 over x squared minus 9. So again, what do we start by doing? Factoring. Can I factor x minus 3?
No.
No. That's prime. Good. Can I factor x squared minus 9? Great. How does that factor? X minus 3 and x plus 3. Very good. Can I reduce this?
Yeah.
Yes. What can reduce? The x minus 3's. So what's left in the numerator? 1. What's left in the denominator? X plus 3. So this, the x minus 3's are now gone, right? That's going to give me a removable discontinuity. This piece that's remaining is going to give me a vertical asymptote. Is everybody okay with that? So far, so good? Here's a question for you. If I can reduce, does that guarantee that I'll have a removable discontinuity? No. Let's see an example of that happening. So let's say we have x squared minus 9 over x squared plus 6x plus 9. First step would be to factor. How does the numerator factor? Great. And the denominator? Good. Anything to reduce? We can reduce an x plus 3, right? Now notice, when we do that, what's left? I have x minus 3 over x plus 3. Did I get rid of all the x plus 3's? So there's no removable discontinuity form because I still have x plus 3's left in the denominator. So the x plus 3 is going to cause a vertical asymptote when I set that piece equal to 0 and so on. Do we have to get an asymptote or removable discontinuity? No, let's look at an example of that. Can I factor x? No, right? That's silly. That's just one thing. How am I going to factor just one thing? X squared plus 1. Can I factor that?
Yes.
No. Why not? It's because it's not a difference of two squares. That's a sum, right? If it was x squared minus 1, we can handle that. X squared plus 1? No bueno. Can't factor it. Okay, so there's no RDs then, right? Because there's no factoring to do. It's already reduced. So if I set the denominator equal to 0 and solve, that should give me my vertical asymptotes, correct? So we'll subtract 1 from both sides, square root both sides. What's the square root of negative 1? No, plus or minus I. Is that a real number? No, it's imaginary, so it's not going to give me a vertical asymptote out of it. So if the denominator has no real solution, it can't be equal to 0 anywhere on the number line. It's not going to create a vertical asymptote. It doesn't create a hole in our domain. This thing is continuous the whole way through. You could draw this with one curve. Okay? I think that's the time we have. This looks like a good place to stop. Let's not worry about any homework from 14. Just worry about the test for next week. Okie dokies. All right.